All right, my friends, we're going to go through some exam problems using Hess's law and heats of formation. This is common in thermodynamics and general chemistry. This is geared towards a general chemistry class, but may be applicable to physical chemistry second year or physics as well. And we're going to start off with Hess's law. And if you know me, I like to jump right into the questions, right into the potential exam questions that you'll get. And this is one exam question right here. So we're given these chemical equations here. We have three chemical equations, and we have the change in enthalpy, the standard change in enthalpy. This sign superscript means it's at one bar, pressure 1 bar, and we have these change in enthalpies for each reaction of these three, and we want to know what the change in enthalpy for this reaction is. Now, if we look at this reaction, CaCO3, we don't have this reaction here. So we're going to need to manipulate these three equations in order to get this one, if that's the balanced equation. So if we look at this, we have calcium carbonate on this side here, and over here on these three equations, we have calcium carbonate as a reactant. So that's good. This is on the right side. Now we have HCl here. So HCl is as a reactant as well in these three reactions. And then for the other side here, we have calcium chloride, CaCl2. This is a product, and this is a product as well. On this side, we have water, and water is here, and then CO2 is here. Okay, so all the reactants are on the reactant side, and all the products are on the product side for these three reactions. So if we add up these equations, just like literally add them up, and I'll make some room here. If we add them up, then what would happen? Well, this wouldn't cancel, would it? See, we would have CaCO3, which is what we want, but then we'd have two of these calcium hydroxides, and we don't even have calcium hydroxide in here. So what we're going to need to do is we're going to need to flip one of these reactions so that these calcium hydroxides cancel out. Now we can't flip this one because this one has HCl as a reactant, and we need HCl as a reactant in the net reaction here. And we need these ones as products in here too. So we can't flip this third one. We're going to flip this one here. And if we flip it, we would have, I'm going to write it below, H2O liquid plus CO solid goes to the calcium hydroxide, CaOH2 solid. And by flipping this reaction, we flip the sign for the change in enthalpy, so negative 67 kilojoules. Okay, so if we ignore this now, and can we add up these three reactions? Well, if we add this one, I'm going to get rid of these to make it a little bit more cleaner. If we add these two reactions together, then we would cancel out this, the calcium hydroxide. We have a CO here as a reactant, which cancels out with this CO as the product. And we have, what else? We have a water here, and we also have a water here. So this water cancels out with one of these waters, so that our net reaction is going to be CO3, calcium carbonate, which we have here. In the reactants, we just have this. So the 2HCl is here, gas, and then we have one. Did I miss something? Oh no, we're good. We have one calcium chloride, which is here. This is our CO2 here, which is here, and then our water is here. So everything balances out. So if we were to add these reactions as is, I'm going to get rid of these here. There we go. Get rid of, just so it's a little bit easier to see, so we're not canceling stuff out. I'll rewrite this. So this is what is this? CaO goes to CaOH solid hydroxide. Okay, so if we have this one plus this one plus this one, we would get this balanced equation. So now that we have the equations in the right order, we literally just have to add up the change in enthalpies of our reactions here. So we'll add that up. 175 minus 198 minus 67 gives us negative 90 kilojoules. So this would be per mole. This is per mole. It doesn't say per mole here. Sometimes they do that, but that's what we have. What do we have? Negative 90. So our change in enthalpy for the reaction would be negative 90 with 2 sig figs kilojoules per mole. Okay, that means every time this reaction occurs, 1 mole of calcium carbonate reacts with 2 moles of hydrogen HCl, hydrogen chloride gas, to produce this calcium chloride. 1 mole of this, 1 mole of this, 1 mole of this. So this is per mole of the reaction, which is also per mole of the calcium carbonate, because there's a 1 here. We release negative 90 kilojoules of heat. Okay, next one here. Now we're going to use, we want to find out the change in enthalpy for the standard change in enthalpy for this reaction here using 2 ways. We're going to calculate it using Hess's law and using the heats of formation. Okay, so we're going to do the first part here using Hess's law, and to solve it using Hess's law, we need some chemical equations. So you'll be given a set of equations on your exam, and you'll be given the reaction enthalpies, which is the same as the change in enthalpies right here. And we want to know what it is for the balanced equation right here. And just a note, I'm working through these problems with you. So I don't have a solution set or a solution manual that I'm working through, a set of notes or anything like that. What you're seeing on the screen is exactly what I'm seeing, and I'm working through it with you. For me, it's more fun. Okay, so what we're going to do is we're going to start at this balanced equation, the one that we care about, this iron 2 oxide, and see where each of these are in the equations that were given. So iron 2 oxide, the FeO is here, and there's no other FeO. So we'll go to the next one, carbon monoxide. Well, we have carbon monoxide here, and here, everywhere. See, the FeO is on the wrong side, and we have too much carbon monoxides on this side. They're not going to cancel. So we're going to need to do some flipping at some point. Let's do another color. Where's our iron solid? So iron solid is here, nowhere else. So this is on the right side. So that's a good thing. And what about our carbon dioxide? Well, we have carbon dioxide here, carbon dioxide here, carbon dioxide here. Okay, so all on this side, but it's not going to cancel out. And now we have some extra stuff, extra molecules that are not in our balanced equation. Let's use, what should we use? This kind of purple magenta color. So Fe2O3, that's iron 3 oxide. Fe2O3 is also here as well. So those need to cancel out at some point somehow because they're not in the balanced equation. And then the Fe3O4 is here. These need to cancel. So I would consider this a challenging exam problem, quite a challenging exam problem actually, because there's a lot of moving parts to it. Now, how are we going to deal with this? Well, first thing that I'm looking at is I want to have all the reactants on the right side. So this one needs to be flipped. We need to flip this. So I'm going to flip this equation here. Oh, I'll put this away. And maybe I'll write it in black to be consistent. And I'm going to zoom up a bit just to save some, maybe so it's easier to see. So if I flip this equation, we'll have 3FeO plus, I'm just going to skip the states. You can't always do that, but since, you know what, I shouldn't do that. This will be solid, this is gas, because we could get into problems if we do that. Okay, Fe3O4 solid plus CO gas. So we flip this one. So now this is on the right side. If we flip this reaction, then this has to be negative. See how we did that? We flipped that. So we're going to kind of X out this one here. So we're going to just ignore this one for now. Actually, you know what? I'm going to make it a white color. So it's like completely gone from our site. Okay, so that's good. And I'll get rid of these as well. Okay, so that's flipped. So we have the FeO solid on the right side. Well, it's the left side, but it's the proper side. And we have the CO2. This CO2 is going to cancel partially with these. Okay, and this Fe3O4 is on the wrong side as this one. See, this not going to cancel. So what we're going to do is we're going to flip this one as well. We're going to flip the first equation. So this equation we're going to flip. So we'll make it black, and 2 Fe3O4 solid plus CO2 gas goes to 3 Fe2O3 solid plus CO gas. And if we do that, we also flip the reaction enthalpy because it's now going the other way. Okay, so this is gone here out of our life. And let's see how we're sitting here. I'm going to get rid of this cursor. I don't know about you, but I don't really like seeing the cursor too much. Okay, so we have iron oxide on this side. Now there's too many iron oxides, but that's okay. We'll deal with that later. We have CO2. This iron solid's on the right way, CO2. Okay, now this one doesn't totally cancel out. See the F3O4? We need to half this or double this. So what we're going to do is we're going to multiply this reaction by 2. And I'll make it black just so there's not too many colors going on. Multiply this whole thing by 2. See, I need to do that because I need to cancel out the iron 3 oxide here, or the iron 3O4. Fe3O4 has to cancel out. And there's 2 here, but there's only 1 here. So we're going to multiply this whole thing by 2, and we're going to multiply this whole thing by 2. So then this cancels out. We have the iron. This isn't going to cancel out on this side. So this one would cancel. So actually, let's cancel that. This cancels, and this cancels. But this one, these two don't cancel. The Fe2O3, those don't cancel. So we need to multiply this one by 3. 3 times, and this would be 3 times. So if we do that, then now we can cancel out the iron, the Fe2O3. So that's cool. And you know what? Let's see what we got. I think we might be close here. If we find out what the net reaction is, we have, here's a CO2 up here, and there's CO, this is CO, so we have a CO here and a CO here, but there's 2 CO2s here. So this CO2 plus 2 of these CO2s, because this is 2 times everything, gives us 3 CO2s, and we still have this iron 2 oxide, which is by itself. Now there's 3 of them times 2, so we have 6 of the iron 2 oxides, FeO. And so that's done. That's done. We have these COs, and there's 3 COs here times 3. So that means there's 9 COs. And okay, I think that's all on the reactant side. Now on the product side, we have this iron here. So I'm just going to write this. Now there's 2 here, but this is times 3. We got to remember to multiply by 3. So that's 6 Fe solid plus CO2. So we still have some CO2s here. 3. We have 3 here times 3. So 3 times 3 is 9. So we have 9 CO2 gas. And then the iron's gone, CO2's gone, and then all that's left is the CO. We have 1 CO here plus the 2 COs, so 3 COs. CO gas. Okay, so that's adding that up. Now these are change in enthalpy, reaction enthalpies here. Now let's see if this gives us what we want. Oh wait, let's cancel out these CO2s here. So these 3 CO2s are going to be gone, and then this will go down to a 6 because we'll just take 3 away. Okay, and that gives us, if we write it out here, I'll go to black. Okay, that gives us 6 I'll just kind of write it out nicely. 6 FeO solid plus 9 CO gas goes to 6 Fe solid plus 6 CO2 gas plus 3 CO gas. Now we did these changes, the enthalpy changes here, reaction enthalpy changes, so we can literally add these up to get the reaction enthalpy for this reaction. So this delta H naught is going to be the sum of these. So we'll plug that into our calculator. Okay, 48 plus 3 times negative 23 plus 2 times negative 22. So the reaction enthalpy for our reaction is negative 65. So negative 65 kilojoules, and that's kilojoules per mole of this reaction. And let's compare that to our actual reaction. We have 6 CO, CO2, CO. Oh, look at this. So we have these COs. We can cancel these COs. There's 9 COs here and 3 COs here. So actually we can cancel this out. This will be a 6, and then this will be gone essentially. So we can change this bottom one here to a 6, and this one is now gone. Okay, so we're looking really close, aren't we? We're looking really close. The only difference is this is 6 times. The one that we have is 6 times the one that we want. So we're going to divide everything by 6. And we got to do the same for our reaction enthalpy. We'll divide it by 6. So we'll just take that and divide it by 6. I still have the equation from last time, so I don't have to delete it. And start again. Negative 10.8. So negative 11, 2 sig figs, we'll just say negative 11. So this reaction enthalpy is, and I'm going to get rid of this question mark, is negative 11 kilojoules per mole. Phew! All right, well, that hit on a lot of little parts, moving parts and innuendos for this Hess's Law example. Hope you enjoyed it. Let's check out part B. Okay, in part B, we're going to do the exact same thing, but find the reaction enthalpy a different way using the heats of formation. And I'm going to lay this out at first, similar to Hess's Law. So I hope you appreciate how I've laid this out. And then after laying it out using Hess's Law, showing you how equivalent they are, we'll go to the shortcut equation. Okay, so we can also determine the reaction enthalpy by using these heats of formation. And this is essentially the amount of energy as heat that's required to make each of the molecules here from the raw elements. And I have a little table here. You might have seen this in the textbook, but by definition, it takes no energy as heat. There's no heat required in order to make pure elements in their reference state. So silver solid, there's 0. This is like the reference state that we base making our molecules off of. So for bromine liquid, it's 0. Carbon graphite is 0. These are like the raw elements that we're going to make our chemicals from. If it's in a different allotrope, like a different type of carbon, so carbon diamond does have a heat of formation. So there is a heat of formation to make carbon in diamond form from graphite form. And if we look here, we can make CO2 from the raw elements in their standard state based from their reference states here. These ones, heats of formation are 0, but to make this, it releases this much energy as heat under constant pressure. Same thing for the iron 2 oxide, and then the same thing for the carbon monoxide here. So if we rearrange this just like Hess's Law, it'd be another way of doing heats of formation, and then I'm going to show you how we don't even need to use Hess's Law afterwards. But I'm using this as a bridge, kind of a gateway into it. So to make CO2, the reaction enthalpy formation is here. So if we use this like Hess's Law, here's our CO2. This is a product, so that's good. Now, iron solid is here. It's already in its reference state. So the heat of formation is 0 for this one. For iron oxide, now iron oxide here is a product, but here it's a reactant. So we need to flip this one around. And if we flip this one around, then this becomes positive. And carbon monoxide, again, we want that to be flipped around so that it's in as a reactant because we have a reactant here. And if we flip this around and flip this one around, we'll see that this O2, there's one O2 here, cancels out with both of these half O2s, and the carbon solid will cancel out with this carbon solid because this is on the other side, and we'll get this net reaction here. So we can just add these numbers up, which I will do right now with our calculator. And hopefully we'll get a number that's close to what we had before. So negative 394 plus 272 plus 111 and negative 11. Two sig fig, so it's actually bang on because there's not much precision with two digits, but that's okay. So negative 11. So by adding all of this up, we get negative 11 as expected. Now, we don't need to use Hess's law. This is kilojoules per mole. Okay, now we're going to solve for the reaction enthalpy using heats of formation without manipulating these equations like Hess's law, and I'll show you that it's equivalent to doing that. So we're going to use the equation which you likely have seen. It's equal to the sum of the reaction enthalpies or heats of formation of the products minus the formation enthalpies of the reactants. And I should put a little stoichiometric coefficient here, because if there's 2's and 3's in here, then we got to put the 2's and 3's here as well. The next example has those. This one, everything is just 1, so kind of nice and easy. Okay, so the heats of formation of the products. So I recommend putting a nice big bracket here, and we'll sum everything up. Now, this is 0. The enthalpy of formation of iron solid is 0 because it's in a standard state. So 0 kilojoules per mole plus the enthalpy of formation of CO2 is negative 394. And you would get this, if you don't know what it is, you would get this from a table. The heats of formation, they're from a thermodynamic table. So that's a negative. So I'll make this negative 394 kilojoules per mole minus big bracket. And you want to have this bracket, this parentheses here, so you don't lose out on distributing this negative sign throughout. Okay, so the heat of formation of FeO is now straight up. We're going to use this as it is because we're not going to flip it or anything like this. So the heat of formation is this number here, negative 272 kilojoules per mole plus, and this is a negative, so we'll turn that plus into a minus. So negative, the heat of formation of CO is 111 kilojoules per mole. Awesome possum. Okay, so we'll plug this into our calculator. And 0 minus 394, just negative 394. Minus, I'm just writing it as I see it, 272 minus 111. And we get, there we go, negative 11. So it's the same thing. And the reason it's the same thing is we're basically just adding this up. We're adding these up, but we're just looking at the products minus the reactants, which is the same as kind of flipping these around because this minus sign is here to flip them around. We get the same answer. Okay, last one to show you how easy it is to calculate the reaction enthalpy or change in enthalpy or heat of formation for a reaction. All of that means the same thing. Heat of formation for a reaction using heats of formation. This is so easy, so we will say the reaction enthalpy is equal to, I'll write the equation out just so we see it. Now this stoichiometric coefficient is important, and it's the enthalpy of formation of the products minus the sum of stoichiometric coefficients times the reaction enthalpy of the reactants is, now let's do the product. So nice big parentheses here. We'll start with this one. So there's a 2. So that's what this V stands for, this 2 here. So 2 times, now what's the enthalpy of formation of iron 3 chloride? Well, we'll go to our table. You would have one like on a cheat sheet or whatnot to look up on, or it would be given to you. So iron 3, FeCl3. Just going to do a search FeCl3, and it's solid. And what's this? I think it's the first column. It's the first column here. These are other variables. FeCl3. So where is that again? FeCl3. Here it is. So negative 399.5. So times negative, we'll make this a square bracket, 399.5 kilojoules per mole. Plus, because we're summing up all the products, 4 times now H2O gas. So we'll look at where H2O gas is. H2O gas is right here. Oh, where did my water go? Uh-oh. Here we are, H2O gas. So negative 136.3 times negative 136.3 kilojoules per mole. And that's all the product. So we'll close the brackets minus big bracket. Don't forget this bracket. Very, very important. We'll do this one. This is a 1. So 1 times. I'll just put the 1 there anyways. We don't need it. So Fe3O4. Let's see where Fe3O4 is. Fe3O4. Negative 1118.4. Negative 1118.4 kilojoules per mole plus 8, because that's the coefficient there, HCl gas. So we'll look for HCl gas, HCl. And this is where the state is really, really important. That's why I was kind of a bit of a stickler on myself. We want to make sure we're in the right phase, because if we have HCl gas has a different enthalpy of formation than HCl aqueous. So we got to make sure we're in the right state. Gas is negative 92.3. So negative 92.3 kilojoules per mole. It's always great to put the units in there. Helps for sometimes if we mess something up. Okay, let's plug this into our calculator. 2 times negative 399.5 plus 4 times negative 136.3. And I think that's good. Minus, that outer bracket's not needed, but we'll have it there anyways. 1 times, which you don't need the 1, but that's okay. I'll put it in there. 111.8.4 plus 8 times negative 92.3. And I include this parentheses for this negative so the calculator doesn't think it's a subtraction. And I think that looks all good to me. Let's see. Okay, so 512.6. So that's our reaction enthalpy, 512.6 kilojoules per mole. We'll round it off to, let's see, these are all 1 decimal place. Yeah, 1 decimal place. So we're good. So here it is using the heats of formation. All right, y'all. I hope you enjoyed it. We went through how to calculate the reaction enthalpy using Hess's law, using heats of formation. I worked through some hard exam problems and some not so hard exam problems. So hopefully you're ready for your exam. Hope you got some benefit from it. Thanks so much. And I got so many other videos on thermodynamics, like onslaught of videos. Check those out. Also with other areas of chemistry and physics and math and whatnot. Thanks again. See you in the next video. Cheers.